Okay, so now I'm going to give you another number that's in here. And it turns out there's not very many nice fractions, and by nice fractions I mean ones that have finite decimals when you write them out in base 10. The 1/10 is also in the Cantor set, it turns out. 1/10. Now, I gave you a kind of a fun way to think about 1/4 right at the end of the last video. Can you think about an interesting way to think about 1/10 in a way that might help you write it in base 3?
Well, 10 is indivisible by 3 at all. Maybe, well, 10 is 3 squared plus 1. So you could think about it, you could think about something, your 1/10 equals x in base 3, and then that x squared, or not x squared, 9 times x plus x equaling 10x, and that equals 1.
Yeah.
So that would be equivalent to shifting 2 places to the right, and then adding your original thing.
Mm-hmm. And when you do that, when you take your original thing and shift it 2 places to the right and add it, what base 3 number do we expect to get?
1, which equals 0.22222.
Okay. Alright, so cool. So see if we can figure out what number pattern satisfies that.
Should be shifting 2 places to the right and get this.
Sorry about that.
So you're gonna need to have some zeros at the start, just because the 1/3 and 1/9 place are both bigger than a 10th.
Yeah.
And then these are gonna be, you need to be able to fill these with 2's once you shift over 2 places, so it's going to start with 2, 2, and then I guess we could also have, or we'll start with 0, 0, then 2, 2, and then that could be our sequence, because shifting 2 places to the right would create 2, 2, 0, 0, 2, 2, 0, 0.
Yeah.
And then adding them.
And so now it's just a question of figuring out if that's 1/10, but
it looks like it, because if this is a 10th, this is 9/10, and they add to be 1.
very good. We don't actually have to do the calculation because your math up here showed it. So that's pretty cool, huh?
Yes.
And the other one, where it was 1 over an integer that's in the Cantor set, is 1/40th, but we don't need to go through that. But also, can you see another number? Now that you know that 1/10 is in the Cantor set, and you know 9/10 is also in the Cantor set, can you see another number that must be in the Cantor set? Now that you know that 1/10 and 9/10 are in it?
1/10 and 9/10. Would 3/10 be in the Cantor set? But it would still have no 1s, because you're just shifting it 1 place to the right.
Very good. So 3/10 is in the Cantor set. Which means what other one is in the Cantor set?
3/10. 3/10. 1/10. 3/10. 9/10. Shifting, dividing by 3, like shifting this way, would get 1/30th.
Yeah, and the interesting, you're right, 1/30th would be in the Cantor set as a result of that, but that actually doesn't have a finite decimal, so that wasn't part of one of the numbers that was in the thing. But that's fine, but there's another 10th that's in the Cantor set. Now that you know that 1/10, 9/10, and 3/10 are in there, you know one other one is in there.
10th. 7/10
Why?
because they have to add.
Yeah.
3/10 would look like 0.0220022, and then 7/10 would look like 0.20022, and so on. And they have to add to be 0.2222222.
Good job. Yeah, that was really nice. That was cool. I thought it was a really fun fact that there were, I forget actually how many it was. I think it was 17 numbers that had finite decimal expansions are in the Cantor set only. Somebody proved that it was just those numbers. Maybe it was 14, I forget exactly, but there weren't that many. And the interesting thing, the question that caused it is 1/4 is the only power of 2
Okay.
that's in the
Yeah.
Cantor set. Okay, good job, man.